Okay, so let's take a look at some final exam review problems. All right, let's start here with number 1. So for f of x equals x squared from 0 to 1, including 0, and x plus 1 from 1 to 2, including 1. So we have this piecewise function here, and the first question is, what is the domain of f of x? Okay, well that is pretty clear that a piecewise function, its domain is really defined over here in pieces. So it looks like we start at 0, including 0, and we go up to 1 for the first piece, and then we start at 1 for the second piece, and then we go up to, but not including 2. So looks like we have 0 to 2 open on the 2 end. The next question is, does the limit as x approaches 1 of f of x exist? If so, what is it? Okay, so if we're going to look at x approaching 1, notice that 1 is the place where these two pieces potentially join up. So we're going to have to look at the side limits here. So let's look at the limit as x approaches 1 from the left, and the limit as x approaches 1 from the right of this f of x. Now, when you're on the left of 1, you'd be in this region here. So my function would look like x squared. And yet when I'm going from the right, then I'd be in this region here, and so it would look like x plus 1. Okay, so I see that in this left limit here, I would get 1 squared, or 1, and in the right limit here I'd get 1 plus 1, I'd get 2. These are not equal, therefore the limit as x approaches 1 of f of x does not exist. Okay, we would need both side limits to exist and be the same. They both exist, but they're not the same. So the limit does not exist. So is f of x continuous at x equals 1? No. Remember, for continuity, we need 3 things. We need the function, well, in this particular continuity of 1, we'd need f of 1 to exist. We would need the limit as x approaches 1 of f of 1 to exist. And we would need the limit as x approaches 1 we'd need, that would be limit as x approaches 1 of f of x. And then we'd need the limit as x approaches 1 of f of x to equal that f of 1. Okay, f of 1 does indeed exist because f of 1 would be in here, so f of 1 would be 2. So that's true. The limit does not exist, so we're already out. Okay, is f of x differentiable at x equals 1? No. If it's not continuous, then it's not differentiable. All right, continuity is required for differentiability. Okay, let's go to the next one. All right, here we have a graph of f of x, and we're going to answer some questions based on it, so I'll have to keep going back to the graph here. All right, the first question is, at what x value or values does limit as x approaches a of f of x not exist? So where does the limit not exist? Okay, let's take a look. Obviously here, the limit doesn't exist because the limit from the left and the limit from the right do not agree. At the asymptote there, the limit does not exist. And that's it. Realize the limit does exist there, and the limit does exist there. Okay, the limit is 2 at that point, so that's okay. So it looks like we are saying that the limit does not exist at -3 and at -2. So we'll put those in. And let me just clear the graph to get rid of some of that notation. Okay, next question. At what x value or values is f of x not continuous? Well, certainly if we didn't have the limit exist, then we must not have continuity. So let's go over here, x equals -3 and x equals 2. But we could have the limit exist and still not be continuous. So let's go back to the graph here. And notice here, at 1, we have a lack of continuity. Because even though the limit did exist, the limit as x approaches 1 of f of x is 2. But f of 1 is 3. So these two things do not agree. The limit value doesn't equal the function value there, hence not continuous. So also at x equals 1. Okay, so now about x values where f of x is not differentiable. Well, we need continuity for differentiability, so all of these now come over. -3, 2, and 1, but we still could have a place where it was continuous and yet not differentiable. And that is right here, because it appears we have a sharp corner there. So at -1, that's also a place where not differentiable. Okay. Now the limit as x approaches infinity and the limit as x approaches -infinity. Okay, limit as x approaches infinity of f of x and the limit as x approaches -infinity of f of x. So let's go up here. All right, as we approach infinity, it at least looks from the graph that this is becoming asymptotic to the x-axis. So that would be y equals 0. So that limit appears to be 0. Here, we appear to be going off to -infinity. Now, what does the point 2, 1 appear to be? Well, as best we can make from this diagram, it looks like before 2, we have a curve that's concave down here, and then we have a curve that's concave up here. And although we can't from the graph specifically point it out, let's go with that. That's the inflection point. Okay, good.